realize I didn't record. Okay, so let me pull the chat up so I can see that. And because now we're recording. So I guess I should have gotten in all my profanity earlier. Okay, so the deltoid is coming, the arm's coming down like this. Your arm hopefully is straight, it's not broken. Okay, and that's going to be the torso. So right here is going to be that 15 degrees. That text is way too big for what we're doing, but we're here now, so that's how it's going to roll. All right, ooh, that's not good. So now we're going to draw. Okay, so the arm here is 1 meter and it weighs 10 kilograms. That's a beefy freaking arm. Okay, but if we find that the moment of inertia is at 60% of its length. So that means we're looking, and that's, remember, the center point of it. So essentially our resistance side is going to be equal to, it's at 10 kg multiplied by 9.81, and that's, remember, gravity, guys, multiplied again by, well, it's 1 meter, but the moment of inertia is at 60% of it, so we're actually going to multiply that by 0.6. Okay, does that make sense? So that's our resistance on the way down. But what we have to actually solve for is how far away this is. So now we're talking about doing some trig. Okay, so, and our insertion is just going to be a grand total of 10 centimeters down the arm. Okay, so the next thing we need to do is, because we have our triangle, we're trying to figure out effectively this down here. Whenever I show that, can you guys see my cursor on the screen? Does that show up?
Yes.
Okay, thank you, John. So what we're trying to figure out is how far it is, because remember, we're looking for the line of perpendicular pull. So what we're going to actually take now is, well, actually, let's see if it'll let me. No, it won't. Of course not. We would take this sum here, and we're going to multiply all of it by, because we're talking about the sine, because sine equals the opposite over the hypotenuse. We know the hypotenuse because that's 1 meter long, but we don't know what the opposite is. So hence, we're going to multiply both sides by the hypotenuse. So we're going to go the sine of 15 degrees. Now, up here, in order to figure out our actual leverage, so the other half of the equation, the vertical force is going to be multiplied by that 0.1 meters, because it's 10 centimeters down, also multiplied by the sine of 15 degrees. Now from there, once we have that vertical force, we're going to have to solve for the last part, which is where we're going to have our deltoid force is going to be equal to, because once again, we're only looking for the vertical component. And since it's a 20-degree angle, we're going to have the sine, we're going to have our vertical force divided by the sine 20. Questions, comments, concerns, guys?
Would we be multiplying the sine of 15 times the 10 kilograms times 9.81 and all that on on the force arm side of things?
Yeah, so like effectively, I don't think it's gonna allow me to move. Oh, actually, maybe it will. Haha, yes. This is gonna be cool if I do it right. Emphasis on the word if I do it right. So that's what your final equation for the vertical force is gonna look like. So obviously you'd still factor, multiply things out so you can go ahead and get things to go on either side like you want them to. What other questions would you guys like to review? Okay, lifting force a bicep has to produce if it has an attachment angle of 86 degrees and is holding a weight that is 25 centimeters from the elbow that weighs 20 kilograms, and the arm's center of mass is 12.5 centimeters and weighs 5 kilograms, along with attachment of the bicep is 2 centimeters from the elbow. So let's clear all drawings and let's start over. Okay, so we've got the weight over here. We've got the center of mass of the arm. We've got the bicep attachment at 2.5 centimeters, and it's also doing so at 86 degrees. Okay, so what do we know? Well, we know we're trying to figure out the bicep force, and that's going to be multiplied by, now this is just going to give us initially not the biceps force, but it's only going to give us the vertical force. So we're going to have to do one more step. Okay, we're going to multiply that by that 0.25 centimeters. That's why I make it 0.025. So it's meters equals. Okay, now we're going to do two different things here. We're going to have first the weight of the arm, which is 5 kilograms, and we're going to go ahead and multiply that by gravity, which we in turn are now going to multiply that by 0.125 meters, because that's the center of mass of the arm. And then we're going to have the weight in the arm. So you're curling a 44-pound dumbbell. So we have 20 kg multiplied by 9.81 multiplied by 0.25. Okay. So now, essentially, this is the first part of our resistance. That's supposed to be the letter A. Me drawing with my right hand on a touchpad and being left-handed makes things, oh, sorry, I got this reversed. Sorry. This is B, and this is scribble, and this is supposed to be A of essentially how I've got that written up. All right, now that we have that vertical force, okay, we're going to do that same type of situation for the bicep force. That is going to be equal to our vertical force divided by the sine of 86 degrees. Does that make sense to you, Luke? Okay. So torque required to accelerate a rotating object if it starts rotating at 10 degrees per second, increases to 110 degrees per second in 5 seconds. It has a radius of 5 and a mass of 100 kilograms. Okay. So can you guys see the equation slide? Or is it still just showing the whiteboard?
It's still showing the whiteboard.
Okay. Thank you, Roland. All right. Well, the joys of share screen. Okay. So our torque equals our inertia times our acceleration. Or the way to look at it is torque equals mass times radius squared times that acceleration. So we're trying to solve for torque. Now we know our mass is 100 kilograms. We know our radius. Okay, Catherine, I appreciate you throwing yours up. We're going to go ahead and get through Zaria's, or talk through Zaria's first, then we'll go ahead and get to yours. And the radius is 5 meters. So we're just going to do that twice. I mean, we could write in 25 or 5 to the second power. You got options. And then, okay, the acceleration is going to be, we went from, and then notice we have brackets. So we have, and we're actually going to go double brackets. We have 110 minus 10 divided by 5. Oh, that bracket's wrong. And then that's going to give us our total torque. So, I mean, we'll just take this thing to its conclusion. Equals 252500, because that's going to be our inertia, multiplied by 100 divided by 5 gives you 20. So torque is going to equal it's a lot of Newton meters. So now for Catherine's, what is the angular acceleration of an object? Notice everything there is set up as the same, but the key difference is our acceleration. Well, no, it's fine. You guys are here to learn, okay? So our acceleration is simply going to equal our final velocity minus our initial velocity. That in turn being, sorry, I messed up my order of operations. Brackets up, divided by 5. So in Catherine's question, it's going to be 90 divided by 5, which is going to give us 18 degrees per seconds squared. All right. So the next question we've got is going to be from Braden, which is how fast would you have to jump off the ground in order to get 10 meters in the air? So this is going to be that simple potential energy equals kinetic energy. So mass times gravity times height is going to be equal to 1/2 of the mass times the velocity squared. So here, since we got mass on both sides, masses cancel. So we've got gravity times height equals 1/2 of the velocity squared, because we don't plan on vomiting while we're in midair, or hopefully not, that'd be bad. And we know in this example, gravity, because we're doing this on Earth, is 9.81 meters per second squared, multiplied by the height, and the goal is to be 10 meters in the air. And then we're going to multiply that by 2. So now we have equals velocity squared. Since multiply each side by 2, we're going to be left with velocity squared equals this. So our final equation is going to be velocity equals the square root of 9.81 times 10 times 2. Does that make sense, Braden? It's okay. Cool. All right. So next question from Sarah. So we're going to draw our lever. Oh, God. Boy, howdy. The effort arm is 20% closer than the point of insertion. So the point of insertion is here, but we're actually going to be 20% closer. So we're going to actually be more like here. And the resistance is 10 kilogram block, 0.45 away. Okay, and so this initially is going to be 0.12. Okay, so what we're going to have here, guys, is our effort multiplied by 0.12. But since we're going to be 20% closer, what should I then multiply this by? Yes, Braden, exactly. Multiply that by 0.8. Same thing, Zaria and Rollin, great job. Equals, okay, that 10 kg multiplied by gravity, multiplied by gravity, which in turn we're going to multiply by 0.45 meters. Anytime, Sarah. What other questions would you guys like to talk your way through? Where does the force need to produce on a lever if it has a resistance arm of 0.9 and 35 kilograms of resistance, and the force produces 50 kilograms to keep this in balance? Cool. So this is looking at it from a different direction, where let's just imagine we've got a bar that's however long. We know the resistance on one end is 35, and we know a resistance which is going to be somewhere over here is going to be 50. Now we know that the fulcrum for this side is going to be 0.9 meters. So what this gives us a formula of, if we have 50 And we can do the times 9.81, but it's going to cancel on both sides. Time the effort arm, which we don't know, equals 35 times 9.81 times 0.9. So you would then have a final equation of the effort arm equals, open parentheses, 35 times 0.9 close divided by 50, because we have 9.81 on both sides and they're going to cancel out. That's a happy sound. Does that make sense to you, Zaria? Yes, unless it gives you the force already in newtons, Braden. If it gives you the force in newtons, then you don't have to use gravity. Because if anything, the fulcrum or the amount of force you'd have to produce as far as pushing down on that fulcrum would obviously change if you happen to be on literally a different planet. So Catherine's question is, how much force has to be produced by the force arm if a lever has a resistance arm of 0.75 and 20 kilograms of resistance, and the force arm is 0.03 from the fulcrum to keep this in balance? All right. So we've got 20 over here. We know that distance is going to be 0.75. And we know this lifting force is just going to be really tight over here of 0.03. So our effort is going to be multiplied by 0.03 equals 20 times 9.81 times 0.75. So then we're going to get the final equation of effort equals 20 times 9.81 times 0.75, and then all of that is going to be divided by 0.03. All right, so I think Catherine's probably good. Or does that make sense? Cool. All right, so yeah, look at that ball drawing skills. So cool. The ball is moving at a grand total of 10 meters per second. And it has 3 meters to fall back to Earth. So right now, the total energy here is going to be equal to the kinetic energy plus the potential energy that this ball has. So we'll just say total E equals, well, 1/2 of the mass, which is going to be 5 kilograms, multiplied by 10 squared, because that's going to be our kinetic energy, is 10 meters per second. Plus our mass again, which is going to be 5, times gravity, times 3 meters off the ground. Luke, we answered that at the very beginning today. You should expect the math we've been doing so far. So it's going to be a combination of obviously a lot of algebra, a little bit of trigonometry. It's going to be the application and going through problems like you guys had in both your take-home assignment, and then obviously what you guys can see on your study guide. That's okay, Luke. I'm okay with leaving it as next Thursday if you're down for it, Haley. And by you, I mean the entire class, guys. You guys want, we can take it on Thursday. Otherwise, we can, honestly, I like the idea of kind of spending a little bit more time reviewing on this, but more importantly, giving you guys the opportunity to effectively, kind of practice this a bit more. And then honestly, more time for you guys to work on your projects. Sounds good, guys. So like anything else. Awesome. So Braden has a question of the angular motion in an athlete that is swimming forwards. Well, remember, angular means rotation about a joint. So it's in the shoulders because you're swimming through. It's in the legs and the hips because you're kicking, so your legs are going back and forth. And you're going to have perhaps some angular motion in the torso going side to side. No, the math portion you guys are able to do as a group also. The math is take home. Yes, back, legs, and hips are all going to have, rotational movement as you're swimming through the water. Angular momentum of an object that is spinning at 30 degrees per second with a radius of 2 meters and weighs a grand total of 50 kgs. So angular momentum is going to be R, where it's H, equals R inertia times our angular velocity. So H equals mass times our radius squared times angular velocity. So in the example that Zaria brought up, this is going to be equal to 50 times 2 squared times 30 degrees per second. Awesome. So Haley, the key difference between the one that you brought up now and the one we did previously, and Zaria, does that answer your question? Awesome. In that the previous one, it was the arm in that angle, so we had to add in that extra trig. This one that you've got, the arm is just straight perpendicular. My God, my drawings are bad. It's going to be just straight perpendicular to the floor. So all you don't have to do all that sine stuff earlier to find that perpendicular force production, since we're only at that angle. Since we're straight out to the side, now you can effectively just go ahead and run the math. So that one ends up being a lot easier because we're effectively have our effort. It's going to be multiplied by that insertion. Where's the deltoid insertion part? I don't see that. Oh, 5 centimeters. Thank you. Equals, and then we're going to have the brackets. So 5 kg arm multiplied by 0.751, because that's the length of the arm, multiplied by 0.6, because moment of inertia is at 60% of its length. Close. And then from there, we're going to take, and the deltoid force is going to equal that effort divided by the sine of 10 degrees. Because the deltoid itself is going to be pulling in this type of angle. It's going to be, oh God, it's going to be even shallower, so more like this. All right, so I'm going to have you guys work in breakout groups. And what you guys are going to go ahead and do, okay? So we're going to kind of think through the amount of force that someone has to produce. And the example here, it's going to be in the bench press. Actually, we're going to call it the midpoint, but it's going to be slightly inaccurate, okay? If they are lifting, we'll say 100 kilograms. The upper arm is 0.4 meters long, and the pec insertion is going to be 0.075 meters down the arm. How much force does the pec need to produce? So let me go ahead and draw this out for you guys real fast. So what we're talking about here is if we have the bar, oh God, and we've got the person gripping the bar and their arms are going to be at that midpoint. And so effectively their head would be in the center here. So the arms themselves, like this would be the shoulder joints. So the pec is pulling here in a relatively slight angle. So first you can just figure out the force that's need to be produced there, because obviously the bar itself is pushing the elbows directly downward. We're not even going to throw in the weight of the hands, which would obviously be additional weight that has to be lifted. And then the next part you're going to figure is the pec itself. And the pec itself is pulling in a 20-degree angle. Does this make sense to you guys? So I want you guys to start off with this, and then I want you to try to, solve both parts of this question. Okay. So I want you guys to go ahead and try to solve that in a group. We're going to put you guys into just 4 separate groups. You guys are going to work together. Now, after you guys solve for that, I want you guys to go ahead and try the same basic question, only base it on a load that one person in your group can actually lift, and try to figure out how much force would their pec have to produce. Now, obviously in this example, the anterior deltoid would also be assisting in the movement. It wouldn't just be the pec by themselves, but we're just doing this to make it a little bit simpler and easier to follow. Sound good, guys? Give you guys, 5 to 10 minutes to kind of work on it in your groups and figure it out. So, actually, before I do that, let me do this. So you guys have got it in the chat now. So you guys can copy and paste it as you need to and use a scratch pad of paper when you're writing it out. So give you guys, let's go 7.5 minutes. You probably need more than 5, but you don't need a full 10. But go ahead and talk with your partners, try to work your way through it, and do your best. Okay. See you guys back in a few minutes. Have some fun. We're waiting on those last few folks to go ahead and join us again. Go ahead and paste into the chat the answer that you guys came up with for each of the 2 questions. Great job, guys. Great job. Did you guys have a chance to try to do it from the perspective of one of the actual folks in your group? My apologies for interrupting you guys on it. That's okay. It's interesting how strong muscle actually is when you actually think about this is just a 220-pound bench press. The world record in the bench press is over 700 pounds now. It's pretty easy to find somebody that can bench press even over 300 pounds. So the amount of force that your pecs actually produce while lifting is pretty impressive. Mind you, that's also in conjunction with the delts and the triceps to a lesser extent. Any questions here? Any questions? Awesome. So let's have a little bit more fun. What exercise would you guys like to do the same thing with? What exercise would you guys like to also break down and do the same type of analysis of? And notice, guys, the amount of force you solved for was literally just the amount of force you need to keep that bar from going down any further. That's just holding that bar in that position. To lift it, you have to produce more than that amount of force. Does anybody have an exercise they would like to go ahead and look at with this? I'm open to ideas because this last one's going to be gnarly. If you guys don't come up with an idea in the next couple moments, because then I'm going to write in one that's going to be difficult. Okay. I like Cass's idea of the squat. Okay. So we're going to have someone, they're going to be, in the bottom of the squat where they're effectively going to be parallel. Okay. So the weight's up here on their back. They've got their head. So we're going to look at the force of the quads trying to extend the leg back up. And we're going to look at the force of the glutes trying to extend the hips. So let's say, well, how to say? I know because we're going to say the thighs themselves are 4 meters in length. They're going to account for about a grand total of 10 kilograms of mass. The center of mass of the torso plus the arms and the head is going to be at effectively, you would have to do the trig for the angle, but I'm going to give it to you anyway. So it's going to be at 0.2 meters. And that mass itself is going to be a grand total of, we're going to go with 60 kilograms. And the load on the back here is going to be 160 kilograms. And it's going to have been a grand total of, let's go with about also 0.4 meters away. And the center of the mass thighs is going to be at 0.2 meters. So in the bottom of this squat, how much force do the glutes and the hamstrings to a lesser extent need to exert in order to extend, to lift the torso and the barbell on their back and then how much force does the quads have to produce in order to lift the weight of the thigh and the torso and the load on the barbell. Does that make sense to you guys? So when you're doing the math, oh, and sorry, the quad itself, the lever arm is going to be 0.05 meters, and the distance of the glute, because I guess we'll say someone's posteriorly endowed, is going to be a grand total of 0.075 meters. Okay, so when you're lifting, okay. All right, guys, this is a lot more complicated. But use what I've given you. We're going to get you guys back into those groups, and I'm going to give you guys a full 10 minutes to work through this time. Okay? Any questions, comments, concerns before we send you guys back in there? All right, guys. So get back at it. I'll see you guys in 10 minutes. Do your best. Make sure you guys kind of think through it, draw it out, and organize it like we've got it here. Have fun. So this stuff gets to be pretty bonkers pretty fast. So the glutes would be equal to 0.075 equals, open parentheses, 0.2 times 60 times 9.81 wrong button, plus 160 times 9.81 times 0.4. And then what gets to be kind of bonkers then is then when we go for the quads, that's going to be equal to 0.05 or multiplied by 0.05 equals open 10 kilograms times 9.81 times the 0.2 meters because it's that halfway point. And then we're going to have plus. Now, this is where it gets weird because we're going to be lifting all of this, but it's through the hip because it's the end of the lever arm where it's attaching. So that's going to equal 160 plus 60. Okay, this is the first function you actually need to do, times 9.81 times 0.4. Does that make sense to you guys? Kind of intense, isn't it? But it's also, I think it's interesting because it looks at, I mean, that's how strong your muscles are. Because when you squat, you're not just lifting the weight of your thighs. Yeah, it's okay, Luke, and that's why you guys are here to learn. But then you have to lift the weight of the rest of your body, and that's all being lifted through, obviously, your hip, because that's where all that weight's being stacked through, the end of that lever arm. So that's all we got for this morning. On Thursday, we're going to spend Thursday effectively working you guys in your groups on your actual projects. So please, 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 if you guys haven't already, make sure you guys get those videos shot of your movement. And then you guys are going to work on breaking down your individual joints and figure out the force. And obviously the squat group, congratulations. I just made your life a lot easier by showing you guys how you're going to go ahead and be able to essentially track and measure all the numbers you're going to come up with. So continue to stay safe out there, guys. If you have any questions, comments, concerns, please let me know. And otherwise, I will see you guys all on Thursday. So have a great day. Stay safe. Bye-bye.